So good evening, everybody. Welcome back to the talks. We have a few talks this session. The first one will be by Ryusuke Jinno. He'll be talking about gravitational waves from first order phase transition.
Yes, I first thank the organizers for kind invitation to this fantastic workshop. Yeah, I'm Ryusuke Jinno from Kobe University, and I will talk about, okay, I think I'm the first person in this workshop talking about first order phase transitions. So I will spend some 20 minutes or so for the introductory stuff about first order phase transitions and gravitational wave production. And then I will explain something, some model distinction from gravitational waves from sound wave sources and free streaming sources based on these four papers. So let me start with the introduction. So I will start with the classification of phase transitions a la Landau. So in this talk, I assume that there's at least one scalar field. Okay, at least in the standard model, we have the Higgs field. And yeah, let's call it order parameter. And as a function of temperature, if the order parameter at the minimum of the free energy Gibbs or Helmholtz behaves discontinuously, then that transition is called first order. And if this behaves continuously, then that transition is called second order or crossovers. And long ago, maybe Higgs was discovered in 2011. I forgot 12. So more than 10 years ago, there were two candidates for first order phase transitions in the standard model. So the left panel is for electroweak, and the right panel is for QCD or chiral phase transitions. And this plot, left plot, is a Higgs quartic coupling as a latent heat from the electroweak phase transition as a function of Higgs quartic coupling. And this is before the Higgs discovery. So the Higgs mass range is 40 GeV, 50 GeV, 80 GeV, like this. And unfortunately, so Higgs was discovered at 125 GeV. So as you can see, as you can extrapolate this plot, at 125 GeV, there's no first order phase transition because there's no latent heat release. And also in this plot, this is for QCD phase transition. The horizontal axis is the baryon chemical potential, and the vertical axis is the temperature. And if you consider realistic time evolution of the universe, it's like this arrow. And this red line, if this arrow crosses this red line, then first order phase transition occurs. But unfortunately, there's an ending point here, which is roughly baryon chemical potential around 300 MeV. So if you consider realistic evolution of our universe, then there's no first order phase transition. So you may ask, why do we first of all consider this kind of first order phase transitions? And my answer in this talk is, okay, so let's imagine the vast energy scale the universe might have experienced from inflation down to the present. And we have 10 to 20 something order, 20 something orders of magnitude difference. And in order to solve particle physics problems and cosmological problems, we sometimes need spontaneous symmetry breaking, like the breaking of the GATT group, Pecha-Quinn group, U1, basically U1, global U1, and also breaking of the B-L symmetry, or dark matter might be produced from the breaking of dark groups. So let's keep open-minded and let's think about the spontaneous symmetry breakings. And some of them might have been first order. So it's not a bad idea to consider first order phase transitions. And on top of that, the process of this first order phase transition is testable in the coming 10 or 20 years with gravitational waves. So I think it's the best timing to start thinking about this. So this is the overview of what happens in the universe if we have first order phase transition. So the left side is microphysics, and the right side is macrophysics. So in the microphysics side, we assume that there's a first order phase transition. Then in our universe, we first find tiny seas of bubbles, tiny true vacuum seas of bubbles like this. And these tiny true vacuum bubbles start to expand because the energy, true vacuum is energetically favored. And eventually, these bubbles collide with each other. And during this process, gravitational waves are produced through this equation, as we learned from the previous lecture. And in the coming 10 or 20 years, we have a chance to detect gravitational waves from this process, like with space interferometers, like LISA, DESI, and so on. So, yeah, this might be a bit too basic, but okay, so let's think about tunneling in quantum mechanics and QFT. So in quantum mechanics, we know that even if your degree of freedom is trapped at a false vacuum at some point, after some time, there's non-zero probability to find this degree of freedom at the true vacuum. And the same thing happens for QFT. So we have order parameter in QFT, which I call phi. And suppose your free energy is like this, and at some point, even if initially the scalar field is localized at the false vacuum, after some time, there's non-zero probability for finding this guy at the true vacuum. But the difference is that in QFT, we have infinitely many degrees of freedom. So at each spatial position, we have, at each space-time position, we have this arrow of phi, scalar field phi. And even if you start from false vacuum, after some time, you find this kind of true vacuum, tiny seed of bubble. This is called nucleation. Sorry, I forgot to remove this Japanese or Chinese. And this is not the end of the story, because once this tiny seed is nucleated, it starts to expand. And in order to understand the bubble expansion, one single phrase is actually enough. Pressure versus friction. This is a toy, how can I say, simplified view of expanding bubble, cosmological size bubble. And the pressure on the wall arises because the true vacuum is favored energetically. Basically, the pressure comes from the released energy. And traditionally, we parameterize this pressure by rho vacuum over rho plasma, defined as alpha. Rho vacuum is, roughly speaking, the difference between the energy density at the true vacuum and a false vacuum. And the plasma energy density is the energy density of plasma. The plasma particles are everywhere in the universe. So this is a dimensionless quantity. And on the other hand, friction arises because the wall is pushed back by plasma particles. And on this point, I think Andrew will give a talk this week or next week? This week? Thursday. Okay. Yeah. And so I prepared some animations. So the horizontal axis is the parameter alpha. And the horizontal, so this direction is increasing direction of the latent heat. So we start from deflagration. So this is the actual profile of the fluid. And this red position is the wall position. So the plasma particles in front of the wall is heated up, and also fluid outward velocity arises in front of the wall. So it's like snowflow. And if you increase the value of alpha slightly, then the wall starts to move faster. So now the plasma particles are heated up behind the wall, and fluid outward velocity arises also behind the wall. And you can further increase the value of alpha, then the fluid starts to behave ultra-relativistically. And then finally, when alpha exceeds some threshold, plasma particles cannot stop the acceleration of the walls anymore, and walls continue to accelerate until they collide with each other. So this is the basic classification of bubble expansion modes. And this is animation, and this is a movie from YouTube for 100-ton detonation or something. And I think you can clearly see the formation of shock waves like this. So each bubble, if first order phase transition occurs in the early universe, each bubble is like this kind of explosion. And we might observe gravitational waves from this process. So this is basically the same as the previous lecture. We start from the Einstein equation, let's say. Okay, so we start from the Einstein-Hill reduction, and we derive the Einstein equation. And it's basically saying that the space-time tells matter how to move, and matter tells space-time how to curve. That's it. And if you take TTH, gravitational waves are the transverse and traceless part of the metric, living here. Transverse and traceless. And if you expand the Einstein equation, you find that gravitational waves obey a wave equation sourced by the energy momentum tensor. And luckily, the notation is the same as the previous lecture. Lambda is the projection operator. And I think I'm missing minus sign, sorry. And as you may know, Live and Virgo collaboration detected gravitational waves from binary black holes for the first time, roughly 10 years ago. So if many bubbles nucleate and collide with each other, what happens in the early universe is like this. So this is from my old simulation around 2021. And different colors are energy momentum tensor, absolute value of the energy momentum tensor. And the main carrier of the energy momentum tensor is fluid, actually. I will explain this later. But anyway, the important point is bubbles collide and fluid dynamics starts. And if it is, okay, let me stress this. If this process occurs in a very early universe, then produced gravitational waves propagates without being affected by the matter inside the universe. So that, and in contrast, if we use photons, they get scattered by charged particles in the early universe, so they lose the information they originally had. So in comparison with photons, gravitational waves can be a better probe of the early universe. And now, okay, so this is a summary of the ongoing and future experiments, observations for gravitational waves. The horizontal axis is the frequency of gravitational waves, and here, this is 1 Hertz, and this is mil-Hertz. And the vertical axis is, sorry, difficult to see, but gravitational wave energy density per unit logarithmic frequency normalized by the total energy density of the universe. And we often saw this quantity in Sriram Kumar's lecture. And one exciting project is, one exciting experiment is this LISA. And so let me explain. Let me introduce this LISA project. It's an abbreviation for Laser Interferometer Space Antenna. And it's a mission led by IISER and NASA. And the launch is planned in the mid-2030s. And as you can see from this figure, 3 satellites forming an equilateral configuration and in the Earth orbit. And finally, the distance between the satellites is determined by 2.5 times 10 to 6 kilometers. And also, some 10 months ago, I think, the mission duration is 4.5 years, and duty cycle is 82%. These are determined 10 months ago, finally, I think. And you can find the information if you Google with LISA Redbook. Now, let me explain 2 different sources of gravitational waves in this first order phase functions. First, I will explain gravitational waves from sound waves. So, in order to explain this, please remember the spirit of thermodynamics. That is, only a few parameters determine the macroscopic outcome of the systems. So, for example, if I drink this water, I don't care about the motion of each molecule. So only the temperature, I don't know, the viscosity, all these macroscopic property, macroscopic parameters determine the macroscopic outcome. And the same thing applies to this gravitational wave production. So we start from Lagrangian. This is microphysics, particle physics, but the eventually the outcome is gravitational waves, that is the gravitational wave spectrum or gravitational wave non-gaussianity, blah, blah, blah. And in order to translate this Lagrangian into the final gravitational wave spectrum, we often translate Lagrangian into 4 or 5, I don't know, but 4, 5, 6 parameters, alpha, beta, BW, and T star. And I will explain these parameters in the next slides. Okay, the first quantity is the transition parameter alpha. And actually, I explained this already. It's defined as the vacuum energy released normalized by the plasma energy density. It's dimensionless quantity. So yeah, alpha determines how much energy is released in comparison to the plasma energy density. Okay, this is just a bit detailed, but the numerator is the vacuum energy density. And if we think about final temperature effective potential, it's basically the Helmholtz free energy. So we have to use, what was that? The Maxwell relation to translate the free energy into the vacuum energy. But this is just detail. Basically, alpha is how much energy is released in comparison to the plasma energy density. And the next parameter is another important parameter. It's called, I will call it nucleation rate parameter beta. And there's no fixed name for this parameter, actually. It's defined as the Taylor expansion coefficient of the exponent of the bubble nucleation rate here, around the typical transition time T star. And in order to calculate this quantity, we first use thermal field theory to calculate the nucleation rate as a function of temperature first, and then we convert it into nucleation rate as a function of time using Friedmann equation. And one interesting property of this beta is that its inverse, or more precisely, wall velocity over beta gives the typical bubble size at the time of collision. So I will explain the reason using this poor drawing. So let's say this is your Hubble horizon. And at t equals t star, suppose that you find 2 bubbles inside your Hubble patch. These are the first bubbles nucleated inside this Hubble patch. And now imagine, after time delta t, which I take to be order 1 over beta, then this nucleation rate changes by some orders of magnitude. For example, if I take 5 over beta, then this nucleation rate changes by factor e to 5. So this sudden increase of the nucleation rate results in the nucleation of other small bubbles around these first bubbles. So these first bubbles cannot expand anymore. So that's why the typical bubble size is determined by the velocity of these guys times the typical time scale for the transition 1 over beta. So the message is this parameter, Taylor expansion parameter beta, gives the typical bubble size at the time of collision. And the other 2 quantities are roll velocity and transition temperature. And okay, I have more time than I expected, so I will explain this. So roll velocity, it's determined from the balance between pressure and friction. And if you expand, if you zoom in around the wall, what happens is the massless particles impinging onto the wall, and they get massive, or they may emit some gauge bosons or other particles. And this process causes friction to the wall. And the wall velocity should, in principle, be obtained from Boltzmann equation, but unfortunately, we don't have resources. So typically, people often this wall velocity just by hand. And it's regarded as the trade-off between the coupling in the Lagrangian and the velocity. And the final quantity is a transition temperature. And this is determined by your choice of microphysical theory. So these are the main 4 parameters which determines the macroscopic outcome. And the macroscopic outcome is this. I have already shown this animation to you, but I will repeat. And people classify the gravitational wave production from this process as follows. The first one is bubble collision, the second is sound waves, and the last is turbulence. And sound waves, turbulence, they are important at later stage. So as you go down, these elements are important at later stages. So let me explain one by one. Bubble collision is basically gravitational wave production from kinetic and gradient energy of the scalar field or the parameter field itself. And it's dominant only when the transition is extremely, extremely strong. Typically, this kind of strong transition does not occur, but in some limited models, this extremely strong transitions occur. And in kind of reasonable transitions, sound waves are the dominant source of the gravitational waves. It's by definition the compression mode of the fluid motion. And yeah, I already said this. It's dominant unless the transition is extremely strong. And at a later stage, turbulence can or will occur. It's of course turbulent motion caused by fluid nonlinearity. And this is expected to develop at a later stage. And if we combine these three elements, currently we have this kind of gravitational wave spectrum. But okay, so that's fine. But let's calculate ourselves. So this slide shows the rough estimate on the gravitational wave production from this process. And I encourage PhD students to calculate yourself using this slide. This is super simple. So what we find will be big and relativistic objects radiate more gravitational waves. So we start from this wave equation for gravitational waves. It's basically a box of your gravitational waves is sourced by the Newtonian constant times the energy momentum tensor. Here, 16 pi g, so 16 pi is 1. And also minus 1 is 1. And projection, I don't care. So suppose the sourcing time is delta t. So naively, you will integrate over this equation, integrate this equation over the sourcing time delta t. And that's correct. That's basically correct for bubble collision. So let's do this. And so if you integrate over delta t, then what you get is h dot is g tij times delta t, the sourcing time. It's like kicked oscillator. And if you remember that the gravitational wave energy density is roughly Newtonian constant inverse times h dot squared, and you substitute this expression, then you will find the proportionality t squared times delta t squared. And the first dependence, Tij is roughly proportional to alpha, the energy density, the vacuum energy released from the transition. And also the second quantity, delta t, the sourcing time, is proportional to beta inverse because each bubble has the size BW over beta. So as you can see, big means a smaller beta, and relativistic means larger alpha or larger Tij. Big and relativistic objects radiate more gravitational waves. And as I wrote here, gravitational wave production from sound waves behave a bit differently, so I will comment on that. So I'm not sure if this is correct. Please tell me if this is correct. So sound shell. So this is gravitational wave production explanation for the gravitational wave production from sound waves. And the point is that sound shells. So if I say hello and if you say hello, then sound waves continue to propagate without affecting each other. And this happens. So if many people say hello at the same time, then the sound creates the random velocity field. These sound shells overlap, with each other, and they create random velocity fields like this. And this random velocity field continuously source gravitational waves. Okay, now let me explain my or our work. And maybe Thomas Constantin will explain this next week in more detail. So I will very briefly explain. So fluid 3D simulation is a bit hard because of the shock waves and numerical viscosity and also computational resources. So currently, two groups are working on this kind of sound wave and gravitational wave production simulations. And we are one of them. And we are proposing so-called Higgsless scheme. Higgsless scheme means that in this scheme, we don't have order parameter field. So why this is possible, I will explain. In this scheme, we do not solve both the scalar field and fluid, but rather we kind of integrate out the scalar field, which means that we treat the scalar field, we treat this scalar degree of freedom as non-dynamical boundary. And I will explain this in the next slide. So the fluid evolution is basically determined from del mu T mu equals 0. Here, T mu is just from fluid. And energy injection at the wall is parameterized by the vacuum energy density, epsilon false and epsilon true. And if you write down the, okay, let's take relativistic perfect fluid for simplicity. And then the energy momentum tensor is like this. And let's define K mu to be T mu 0. And then del mu T mu equals 0 reduces to two equations for K0 and Ki's. And here, Tij can be re-expressed by K0 and Ki. And depending on the vacuum energy at the false vacuum and true vacuum, the functional form of this Tij takes different, becomes different. So that's where the vacuum energy density difference enters in this system. So we can just solve these two equations. Very simple. And this is a bit detailed explanation, recipe for the Higgsless simulation. So we first numerically generate nucleation points and determine the false-true boundary of these bubbles. We first fix this evolution without putting fluid on the lattice. And then we evolve this system, we evolve the fluid in this box according to these two equations. Then the fluid starts to develop profiles. And yeah, this is the simulation slices from our paper. The first law is fluid velocity, and the second law is enthalpy, and the final law is vorticity. And you will clearly see the formation of shock waves like this. Yeah, and in this simulation, we simulated up to alpha 0.5, and this is, I think, the largest value we simulated in the world. No, maybe second largest, I'm not sure, but this is one of the largest values of alpha simulated in the world. And we observed a fast decay of the fluid kinetic energy. And if you're interested, please see our paper. And the summary of part one is that the Higgsless simulation is now one of the largest simulations in the world. And we are now able to simulate the strong transition regime, alpha order 1, and which was previously difficult due to shock and numerical viscosities. And numerical data suggest that we might be observing sound waves developing into turbulence. And this is a very fantastic thing. This is a summary of part one. Let me move on to part two. This might be more interesting to particle physicists. So far, I have explained three gravitational wave sources. The first one is bubble collision, and the second one is sound waves and turbulence. And let me combine sound waves and turbulence as fluid contribution to gravitational waves. And a question I would like to ask is, aren't we missing one possibility? That free-streaming particles or feebly interacting particles. Because in fluid contribution, particles in the broken phase frequently interact with each other, and that's the reason why these particles can be described by a fluid picture. But if these particles have only feeble interaction, then particles in the broken phase start to free stream. So we expect kind of different, qualitatively different gravitational wave production. So this is the picture we have in mind. Suppose this is the bubble wall. And in the symmetric phase, we have X particle, massless X particles, which forms temperature T and moving with bulk velocity BW, because we are now in a bubble wall rest frame. And these particles impinge onto the wall with temperature, typical energy of the gamma factor times the temperature. And after entering the wall, this particle becomes massive. And because of this transition, the interaction of X particles with other particles might be switched off, or the decay product of this X particle may behave as feebly interacting particles. So either X particle or its decay product Y can be candidates for free-streaming particles. And let's consider this setup. And this animation shows almost everything. The left animation is for first-order phase transition with fluid. And the right panel is transition with free-streaming particles. And I think you clearly see the difference. In the left panel, the sound shell propagates inside other bubbles after collision, as I explained previously. But for free-streaming case, how can I say it? The structure, the bubble-like structure, expand, but they don't. The structures are not like sound waves, obviously. So we expect different types of gravitational wave production from these two systems. And in order to calculate the gravitational wave spectrum, we propose a new calculation scheme, which we call sprinkler picture. And I will briefly explain this. So, okay, explanation is already shown. The blue surface is the bubble wall. And imagine we have sprinklers at each grid point, which splashes particles as soon as the bubble wall hits the grid point. Okay, to explain this, please, let me explain the calculation for gravitational wave production in sound wave case first. This is a recipe for how to calculate gravitational wave spectrum for sound wave case. We first calculate the time evolution of the system like this, and then we translate this time evolution of the energy momentum tensor into the produced gravitational waves through this wave equation using fast Fourier transform or Green function as we learned in the previous lecture. And basically, there's no shortcut. That's the point. Basically, there's no way around in this process because of nonlinearity. Nonlinearity is the keyword. Because, okay, sound waves are linear phenomena. Time derivative squared minus sound speed squared times spatial derivative squared of the fluid velocity is 0. That's sound wave. But in terms of gravitational wave production, this is nonlinear because the lambda Gaussian of IIJ gravitational wave field is sourced by the energy momentum tensor, which has velocity times velocity. So in terms of gravitational wave production, this system is nonlinear, even though the sound waves are linear phenomena. That's the main difficulty of this sound wave system. But in the present case, in the case of free streaming particles, gravitational wave production is linear in each free streaming particle. So box Hij is sourced by the energy momentum tensor, but the energy momentum tensor can be written as simple superposition of the energy momentum tensor from each particle. And that's why we propose sprinkler picture. So imagine each grid point has a sprinkler that splashes free streaming particles when hit by the ball. And the point is the sprinklers are universal. The only difference between this sprinkler and this sprinkler is when and in which direction they are hit by the ball. And for other properties, these sprinklers are universal. And the gravitational wave production from one sprinkler is very easily calculable. And after calculating gravitational waves from each one single sprinkler, we can linearly superpose the contribution from different sprinklers. This kind of simplification happens for gravitational wave production from feebly interacting particles. And I will skip all the details, and I'm showing the final result. The horizontal axis is the wave number of the gravitational frequency of the gravitational waves, and the vertical axis is the amplitude, energy density of the gravitational waves. And after normalizing by some factor, the gravitational wave spectral shape is found to be universal for different particle physics parameters. And here I compare the gravitational wave spectrum from free streaming particles and sound waves. And they have clearly different shapes. For free streaming case, the gravitational wave spectrum stretches over much wider frequencies. So we have more prospects, more possibility for detection. And okay, I will finally briefly comment on particle physics framework. So the message, sorry, I will skip this slide. The message is, okay, realizing this setup from particle physics models is a bit difficult. So if you come up with some realistic setup, then that can be a paper. I'll explain the reason why it's difficult to realize. It's a bit difficult to realize this kind of situation. So for particles to free stream, we have to switch off their interaction. So we need this condition. The number density of the free streaming particle times the cross-section of the free streaming particles with other whatever particles times the typical transition time scale should be less than 1. And this condition is a bit hard to satisfy because okay, now consider X particles gaining mass from scalar field S. Then the fact that X particles gain mass from S field means that there's interaction between X particles and S particles. So that's the reason why shutting off the interaction between X particles is a bit difficult. And I think the only realistic example will be X particle decaying into daughter particles Y with suppressed vertex epsilon. Then the daughter particles Y can free stream. Okay, let me summarize my second part. Gravitational wave spectrum from free streaming particles differ from the spectrum from sound waves because of the nonlinearity of the source. And if we can observe gravitational waves, then its spectral shape will provide us with the information on the nature of the source. Thank you very much.
Thank you for the nice talk. Questions?
During the phase transition, let's say electroweak?
For electroweak phase transitions, for For electric phase transitions, that might be difficult because first of all, we have to realize first of all the electric phase transitions, and also we have to prepare light particles which dominantly carries the energy and free stream. So my impression is it's a bit difficult.
What about Z going to mu?
If nu contains neutrinos are neutrinos are not free streaming during at the scale of electric phase transition. We have to add some new component, new particle component. Yeah, dark particles will do the job.
So what is the coupling that the excess coupling? Small or
Which coupling do you mean? Ah, okay. These are, for example, x square, s square, if they are both scalar particles, and this particle is SBEV. So well, you can choose. You can choose. X, okay, if x is a scalar and s is also scalar, then the vertex has mass dimension 1. Which are okay. So x can be fermion or x can be boson. You can choose.
So the simulations you are doing, is there any the wall thickness? Does it play any role?
Essentially, no. Essentially, no. Except for the calculation of the bubble wall velocity, and I think Andrew will give a talk about it. And once the wall velocity is determined, then macroscopic outcome, I mean, gravitational wave production is determined only from macroscopic property of the system. So I think the wall thickness doesn't matter in that calculation.
So I have a question for you here. Are there flux tubes formed in the simulation? Flux tubes.
Huh?
Flux tubes.
Flux tube. Flux tubes. Oh, you're thinking about some specific type of model? Yeah. What kind of model are you thinking about?
No, if when the particle penetrates a bubble wall, let's say there are patches where of false vacuum, because the bubbles are expanding, those patches get squeezed, and maybe it gets enough energy to penetrate the wall, then you can get a sort of a flux tube.
Yeah, right. Some specific models, in some specific models, that kind of flux tube can appear.
But not here.
Okay. In this calculation of gravitational waves, we just treat the particles as perfect fluid. So that microscopic description is missing.
Okay. Thanks. Are there any more questions?
Yeah. Just a bit offbeat question that if you have a second order phase transition and you have something like a decay of a heavy particle during phase transition, like you are saying, can you still have some sizable gravitational waves?
I haven't thought about it.
Let's say you have a standard model and the Z decays into invisibles.
One of the necessary ingredients to produce gravitational waves is the macroscopic coherence of the source. And yeah, so it depends on, I think it depends on the coherence length of the transition.
So maybe the Higgs decays into an invisible, that will do it?
I think negligible, because that kind of decay occurs everywhere, and it basically makes the system uniform. So if that kind of decay at this point and at this point, so neglect the bubbles because we are now considering second order phase transition, the particle decay at this point and at this point are correlated, then we expect some gravitational wave signal, I think. But if the decay occurs everywhere in the universe, then the gravitational wave signal will be super tiny.
So if there are, okay, good.
So we get rid of the Higgs because using this. How can I explain? So let's think in terms of the gravitational waves produced. So your gravitational waves produced. And if you look at the system, you don't care about, for example, the wall thickness or each particle. You don't care about that. The only thing you care is the vacuum energy at this point, in this region is epsilon true, and the vacuum energy density at this region is epsilon false. That's the only thing you care if your gravitational wave is produced. So in this sense, we are translating the vacuum energy density released by the Higgs field into macroscopic description. I think that's the correct way of saying this.
For a given benchmark point, you are calculating your epsilon f and epsilon t from the microscopic physics, and that is your input towards.
Right.
Okay. If there are no further questions, let's thank Ryusuke again.